The learning objectives are as follows. We will discuss free radical reaction steps, halogenation radical reactions, specifically looking at chlorine and bromine, and also discuss the regioselectivity and the stereoselectivity of halogenation radical reactions. By the end of this presentation, you should be able to identify radical reaction steps, predict the products of halogenation reactions, and determine the regioselectivity and stereoselectivity of halogenation radical reactions. So in order to stop competing reactions, meaning addition to the double bond or addition in the allylic position, we avoid that by using N-bromosuccinimide, which is considered to be NBS. So in this case, we can talk about if we draw the mechanism for, in this case, the bromination of. So now let's discuss allylic halogenation. So allylic halogenation, remember, we have the carbon-carbon double bond effect as well as the carbon-hydrogen bond strength. So when we're looking at this, right? So when we're looking at the allylic radical, so remember, the higher the bond association energy, that means the less stable this molecule. So when we're talking about the allylic here, so we're looking at, in this case, 1, 2, 3. So that means what's going to happen is that we're going to get a more stable radical. So when we're looking here, 1, 2, 3. So when we're current, we see this one. So the lower that bond dissociation energy, that's going to give us the more stable radical. So we see here blue with this position. This is where we can get that allylic hydrogen here. So it's the more stable, so bromination will occur here. So remember, we have that initiation step. It gives us 2 bromine radicals. This is our initiation step. So again, we have that hydrogen abstraction. So we have and so from there we see that this will give us bromination. So we have a halogen abstraction. So we see that bromine will occur at this allylic position. So this is considered to be allylic hydrogenation. Halogenation, sorry. So again, allyl radicals form fastest, and that is because they're resonance stabilized. So remember, the more resonance structures you draw, the more stable that radical is, because that means that radical is delocalized throughout or over more atoms. No one atom is bearing that one unpaired electron. So again, the radical allylic halogenation reaction requires at least 3 key steps. We have that initiation step where we're forming the 2 bromine radicals either through heat or irradiation. Then we have the hydrogen abstraction. These are our propagation steps. And then we can have a halogen abstraction. So remember, when we're talking about halogenation, remember bromine is more regioselective than chlorine. And so again, we look at the regioselectivity, meaning what's going to give me the more stable radical. So step 1, that's the initiation. Step 2 and 3 are those propagation steps. And then again, if we consider allylic bromination reaction conditions, this is what occurs. Bromination will always occur at the allylic position. So when we're looking at Br2, what could actually happen? So remember, this can be a competing reaction because remember, halogenation, so we can have addition reactions to the double bond. So if we just use Br2, so with allylic bromination under these conditions, we can also have addition of the bromine bond, this molecule. So I'd like for you guys to practice doing that. And so now we're going to predict the products of allylic bromination with NBS and irradiated UV lights. So if we look at this structure here, so remember, bromination is regioselective. So that means we're going to identify the position, the most stable. So in this case, we would say here and here, because what we have are, in this case, we can have, these are considered to be allyl radical positions. So again, we identify all of the allyl positions, because remember 1, 2, 3, and 1, 2, 3. So these are our, and then the next step, so one, we identify allylic positions, and then 2, remove hydrogens. So these are my 2 allylic. So now I can remove so forming that radical. So then next, after you do that, we can see this is where bromination will occur. And so after we do that, we can third thing that we would do is draw your resonance structures. So if we look at this structure, and so we get this radical here, we see that this structure is actually symmetrical. So what we have to do is only consider one position. So this is the structures that we would get. So bromination would occur. Sorry, drop that. So this is where bromination would occur. So again, if we do another practice problem, sorry. So the first thing you do is identify the allylic position. Second, remove the hydrogen. And then third, draw resonance structure. So these two plus 1, 2, 3 would be my allylic positions. So first, and if you see, these are basically the same. So I removed the hydrogen, and here I have a radical. So now I'm going to draw my resonance structure. So in order to predict the product, bromination would occur at these two positions. So if I look here, I have, so this would give me a racemic mixture because I have a chiral center. So now let's talk about, in this case, where we look at the peroxide effect. Remember alkene hydrohalogenation. So remember, the way that it should be is that we get the Markovnikov addition. With the peroxide effect, we get the anti-Markovnikov. So radical hydrohalogenation, the mechanism as follows. So with peroxides, we get the heat. So we get our two alkoxide radicals. So then this is our initiation step. We get the hydrogen abstraction. Plus our bromine radical. So then, of course, we can do to give us the addition of bromine So we get the addition of bromine, because remember in our propagation step, we can add to an alkene So once we get that, where we have here, we have that bromo radical that adds to the pi bond, so giving us a stable carbon radical. And so we can then now have the stable radical, which can do another hydrogen abstraction. To give us the anti-Markovnikov addition plus that bromine radical. And then we can actually have the coupling of a bromine that will give us our termination step. So this is the mechanism that will give us, that helps us understand why we get that anti-Markovnikov addition. So now let's do a review where we're just predicting the products for HBr. So this will be a review. I'm just going to do a couple of these. So this is basically a review of addition of alkene reactions. And so this is with HBr, with peroxide. So we know we're going to get let me draw this again since it's this way. with peroxide. So again, this is going to give us the anti-Markovnikov addition. Another example. Now we know the mechanism. So remember here, we now have chiral carbon, so we must realize that we're going to have a racemic mixture. So we're going to get the enantiomer. So in summary, only radical chlorination and radical bromination have practical use in the laboratory. Bromination is generally a much slower process than chlorination. So in this case, I want you to know that halogenation occurs more readily at substituted positions. Bromination is more selective than chlorination. So when a new chirality center is created during a radical halogenation process, both possible stereoisomers are obtained. When a halogenation reaction takes place at a new chirality center, again, a racemic mixture is obtained regardless of the configuration of the starting material. Alkenes can undergo allylic bromination, in which bromination occurs at the allylic position. So remember, N-bromosuccinimide is used instead of Br2 to avoid competing ion addition reactions.